A debugger or debugging tool is a computer program that is used to test and debug other programs. The code to be examined might alternatively be running on an instruction set simulator, a technique that allows great power in its ability to halt when specific conditions are encountered but which will typically be somewhat slower than executing the code directly on the appropriate processor. Some debuggers offer two modes of operation: a full or partial simulation to limit this impact. A trap occurs when the program cannot normally continue because of a programming bug or invalid data. For example, the program might have tried to use an instruction not available on the current version of the CPU or attempted to access unavailable or protected memory. When the program traps, or reaches a preset condition, the debugger typically shows the location in the original code if it is a source-level debugger or symbolic debugger, commonly now seen in integrated development environments. If it is a low-level debugger or a machine language debugger, it shows the line in the disassembly. Features: typically, debuggers offer a query processor, symbol resolver, expression interpreter, and debug support interface at its top level. Debuggers also offer more sophisticated functions such as running a program step by step, stopping at some event or specified instruction by means of a breakpoint, and tracking the values of variables. Some debuggers have the ability to modify program state while it is running. It may also be possible to continue execution at a different location in the program to bypass a crash or logical error. The same functionality which makes a debugger useful for eliminating bugs allows it to be used as a software cracking tool to evade copy protection, digital rights management, and other software protection features. It often also makes it useful as a general verification tool, fault coverage, and performance analyzer, especially if instruction path lengths are shown. Most mainstream debugging engines, such as GDB and EBX, provide console-based command line interfaces. Debugger front-ends are popular extensions to debugger engines that provide IDE integration, program animation, and visualization features. Some early mainframe debuggers such as Oliver and Simon provided this same functionality for the IBM System/360 and later operating systems, as long ago as the 1970s. Reverse debugging. Some debuggers include a feature called reverse debugging, also known as historical debugging, or backwards debugging. These debuggers make it possible to step a program's execution backwards in time. Various debuggers include this feature. The Visual Studio Ultimate Edition debugger offers reverse debugging for C, Visual Basic.NET, and some other languages, but not C++. Reverse debuggers also exist for C, C++, Java, Python, Perl, and other languages. Some are open source. Some are proprietary commercial software. Some reverse debuggers slow down the target by orders of magnitude, but the best reverse debuggers cause a slowdown of 2A, or less. Reverse debugging is very useful for certain types of problems, but is still not commonly used yet. Language dependency. Some debuggers operate on a single specific language while others can handle multiple languages transparently. For example, if the main target program is written in COBOL but calls assembly language subroutines and PL/1 subroutines, the debugger may have to dynamically switch modes to accommodate the changes in language as they occur. Memory protection. Some debuggers also incorporate memory protection to avoid storage violations such as buffer overflow. This may be extremely important in transaction processing environments where memory is dynamically allocated from memory pools on a task-by-task basis. Hardware support for debugging. Most modern microprocessors have at least one of these features in their CPU designed to make debugging easier. Hardware support for single-stepping a program, such as the trap flag. An instruction set that meets the Pope and Goldberg virtualization requirements makes it easier to write debugger software that runs on the same CPU as the software being debugged. Such a CPU can execute the inner loops of the program under test at full speed, and still remain under debugger control. In-system programming allows an external hardware debugger to reprogram a system under test. Many systems with such ISP support also have other hardware debug support. hardware support for code and data breakpoints, such as address comparators and data value comparators or, with considerably more work involved, page fault hardware. JTAG access to hardware debug interfaces such as those on ARM architecture processors or using the Nexus command set. Processors used in embedded systems typically have extensive JTAG debug support. Microcontrollers with as few as 6 pins need to use low pin count substitutes for JTAG, such as BDM, SPI wire, or debug wire on the Atmel AVR. Debug wire, for example, uses bidirectional signaling on the reset pin. Debugger front ends. Some of the most capable and popular debuggers implement only a simple command line interface, often to maximize portability and minimize resource consumption. Developers typically consider debugging via a graphical user interface easier and more productive. This is the reason for visual front ends, that allow users to monitor and control subservient CLI-only debuggers via graphical user interface. Some GUI debugger front-ends are designed to be compatible with a variety of CLI-only debuggers, while others are targeted at one specific debugger. List of debuggers. Some widely used debuggers are Firefox JavaScript Debugger, GDB, the GNU Debugger, LLDB, Microsoft Visual Studio Debugger, Valgrind, WinDBG, Eclipse Debugger API used in a range of IDEs, Eclipse IDE Node Eclipse, WDW, the OpenWatson debugger. Earlier mini-computer debuggers include Dynamic Debugging Technique, Online Debugging Tool. Earlier mainframe debuggers include 1974 IBM Oliver, 1980 Simon, 1985 CASTIST, 1990 Expeditor and Expediter CICS. Current mainframe debuggers, Debug Tool for ZOS, Expeditor and Expediter CICS, ZXDC. See also. References, General, Suniev Kumar Agarwal and M. Sarith Kumar. Debuggers for Programming Languages. In YN Srikantampratai Shankar. The Compiler Design Handbook, Optimizations and Machine Code Generation. Boca Raton, Florida, CRC Press pages 295 a 327. ISBN 978-0-8493-1240-3. Jonathan B. Rosenberg. How Debuggers Work, Algorithms, Data Structures, and Architecture. John Wiley & Sons. ISBN 0-471-14966-7. Specific. External links, Debugging Tools at DMOZ, Debugging Tools for Windows, OpenRCE, various debugger resources and plugins, Parallel Computing Development and Debugging Tools at DMOZ.